Last night I was working on this talk and I was looking in sched.org and I found out that you can look at your popularity of your talks. And this was listed as 47th out of 50 talks in terms of who had signed up to come to it. So I'm glad that there's actually some people here. Maybe waiting 13 minutes was good. I'm going to talk about consistency trade-offs for SDN controllers. And this is sort of, think about it as clustering, HA, distribution, logically centralized, whatever you want to call it. That's why I'm going to sort of try and talk about what we can and can't do and why this is sort of a fruitful area to go work on. So I'm putting this slide up not to argue about it, but so don't argue with me about it. But I admit there are lots of different definitions of SDN, but my personal sort of three premises that SDN went through was one, sort of separation of the control plane from the data plane. That's the ONF standard definition. Second was the logical centralization of the control plane. And last was sort of common abstractions for network devices. This talk is going to be all about logical centralization of the control plane, and in particular, the logical part of the logical centralization of the control plane. And so just before I dive into that, I want to go over why it is that we can't have an actually centralized control plane, because that's what we want. And in practice, we've built the distributed control plane out of a sort of a distributed cluster of controllers when we're building SDN controllers as a general rule. One, so we can tolerate faults. Two, so we can maybe scale out performance. Although I've heard a lot of people talking about that and less people actually showing me that I can't. That I need to do that. In particular, like Dave Ericsson in the front row built a controller that does 10 million flow operations per second on a single server. So if you're planning on, maybe scale out might not be as important, but I'll talk a little bit about that. And then lastly, and this is going to sort of a forward reference to things I'm going to talk about in the talk, if you have a network partition, you hopefully distribute your controllers such that there is a controller on both sides of your partition at the very least. So that way, the devices which are left on the other side can still do something useful. So I'm going to do something probably I shouldn't do in a talk, but I'm basically going to give a 20-minute distributed systems lecture because I've discovered that distributed systems is not very well understood. And hopefully this will let you in 20 minutes sort of get the equivalent of what you would have remembered if you had taken a distributed systems in class in undergrad or maybe in grad school. And so before I dive into that, I'm just going to say a couple of things. First of all, traditionally when people talk about distributed systems, they talk about replicated state machines. I'm not going to talk about replicated state machines, but if you want to go read about them, what I'm saying is actually applicable to them just fine. People typically talk about clients and servers. I'm not going to talk about clients and servers. I'm going to talk about clients and controllers because I just want to keep us thinking that we're talking about SDN, not an abstract thing. And when I say client, I don't mean somebody with a web browser. I mean a switch or a REST, or somebody calling the REST API or tickling things. So these are sort of people consuming services that the controller is offering. So the key idea here is that things are really easy when there's one controller. If two clients talk to a controller, it's the same controller because there's only one. So it's right there. And if they go and ask it something like, say, what color is it? And the server thinks it's green, the controller thinks it's green, it's going to tell both people that in fact it is green. They don't have to worry about what other else might happen. So this is really what we want. This is the model that we are going for. This is what people can understand, they can program against, they can deal with, and they can reason about. So the real question comes down to how do we get n different controllers to behave as though they are one controller? So let's say we have a collection of 9 controllers. I use 9 because you're going to have majorities of things, and it's easier when I don't have to do weird roundings. A majority is 5, it's not 6, but we'll get into that. But if you have n controllers, and they all sort of start off sharing the same idea of what the network looks like, let's say that it's green, then it's all consistent and everything is happy as long as your clients talk to the same controller. They'll get the same idea. So if you have 2 different clients, they both talk to the same controller, same as before, they're both going to find out the same answer to whatever question they might ask. Problems start coming up in this kind of model when clients are talking to different controllers, which is what you actually want to happen, right? You want to have some of your switches bound to different controllers, preferably ones close to them, or at least be able to fail over to ones close to them, so that way if a partition happens, they get that, or maybe they get better latency, or maybe you're just lose less of your network if one controller goes down, so that you minimize the impact of a single controller going down, et cetera. And so in this case, if everybody starts off thinking it's green, everything is fine so far. But if this first client, say it's a switch, updates some state about the network, it says a port has gone down. And so it updates it, and so now the state of this one controller is blue, representing that something's changed. and it's going to actually get that back. So in fact, it sees the network as being blue, whatever that means. That's not going to help this bottom guy. This bottom guy is going to go ask some other controller, and he's going to get back the answer that it's still green. And this is sort of, right, this is the problem we're trying to solve. We have different people doing different things, trying to sort of coordinate their actions, and without some coordination, we're going to get totally different answers, and nobody's going to be able to figure out how to reason about it. So the really simple first fix that people go to use this, and it's not all that simple in practice, but it's simple in concept. You can think of this as Paxos, or you can think about it as two-phase commit, or I guess it's three-phase commit is the other one, is that if each client talks to a majority of the controllers, things are okay. So just to give you an example, let's say this first client, so everybody thinks it's green at the moment, this first client is going to pick a majority, let's say these 5. And he's going to talk to these 5, and he's going to tell them all about his update to the network. This port has gone down, for instance. And now all 5 of these people know that, in fact, the state of the network has changed, which now this port is down, it's blue. The great part is that if the second client also picks a majority, by definition, those 2 majorities will overlap at least one node. So when it asks the question, what is the state of the network, it will get back 5 answers, one of which is the correct answer. And because we are going to use logical timestamps inside of this, we actually know which one is right. So we have data that says the blue thing happened after the green thing, so we can actually go and say blue is the right answer, and we know about it. And so these majorities are great. So right, it's great. Now we have something acting logically as one entity. It provides consistent answers. The clients can sort of figure out what's going on in the network. They can publish state to the controller. They can get stuff back. And we now have one logical entity. We get our fault tolerance. We might get our scale out, et cetera. This isn't in practice how people build this, because getting your clients, like your switches, to change how many things they talk to and then wait for talk to 5 of them, and then maybe if only 4 of them respond back, try to talk to somebody else and repeat. Instead, what happens is you typically confer with, you have the controller who's responsible for the request sort of proxy it and talk to other people. So in this case, you might think of this request, they actually go talk to 4 of their friends to make sure they get a quorum before they then reply and tell this guy what's going on. And similarly down here, you do the same thing. And as long as you share one node in common, then you know that you'll get the most recent state, or you'll not update anything without other people seeing it. So this is sort of this is the core of how it is that you make a consistent cluster. No matter what anybody else does, like if you want something to be consistent across a bunch of nodes, this is basically the only trick, and it's what you do. The one thing that I sort of that this generalizes this is that we didn't actually use the fact that it was a majority. We used the fact that the read and the write sets overlapped by at least one node. And so you can generalize this into things called sloppy quorums, where basically you read and write from different numbers of the people in the cluster, and as long as the read plus write is greater than the number of nodes in the system, then basically you're guaranteed this overlap. And this can help with your scale out or performance, because it lets you essentially tune. If you're a 90% read workload, you can tune it so that way your reads are much cheaper than your writes, at the expense of making your writes much more expensive and potentially less likely to succeed. So anyway, that's my, I think it was about 8-minute introduction to distributed systems and how we actually get clusters to work. If there's any questions, you should stand up and yell at me. Otherwise, I'll keep going on to the next thing. Did that make sense to everybody? Okay. Oh yeah, so this does not, what this promises you is that everybody will see the same timeline, and that my observable actions that take place logically after other things that have happened are also observable to me, or sorry, before. So it's basically, what this says is there's going to be one timeline, everybody's going to agree on it, in which all of the events take place. And if I have observed some point in that timeline, all of the things that came before that in the timeline, I will also get the same answer for as everybody else, and that the things that happen in the future, we will all agree about once they happen, but they might have happened somewhere else and not have happened here yet. Does that make sense?
Yeah, I don't think it's a question, but it's
So the answer is, formally what this is providing is linearizability, which is just that all events will be completely ordered and that people will see the events in those orders. It doesn't actually guarantee synchronization in real wall clock time. And if you want to go look up linearizability, it's worth going and looking up. So the next part is, so great, we've solved the problem. So the next part is where this goes wrong and the CAP theorem. So the CAP theorem is, I'll go into the CAP theorem a little bit next. So where this goes wrong is that network partitions make everything painful. So before there's a partition, let's just say everything goes as before. We have this one guy, he finds his majority, he updates the state of the network, he actually sends it to everybody, and so now we're in the point where we were before. We have a majority of the network believes the state has updated, therefore it is true as long as everybody else can query a majority. The trouble comes up if you have a network partition. In this case, we have a partition between everybody that knew about the change and everybody that didn't know about the change. You could have different partitions, it doesn't really change things. But if you have a network partition now, the clients on this side are faced with a problem. So they're gonna go find their majority, and they're gonna ask for what it is that they can get. And they're going to get back the full responses with the old state. But this link to get the new state from the overlying member doesn't exist anymore, right? That's partitioned. We don't have a way to get there. And so when we go to get this, it's just not going to make it. And so we have two options at this point. We can either try other people. It turns out there aren't any other people to try because of the network partition. Or we can return the value that's old and just knowing that it might not be the newest value and warn people, or not warn people as the case may be, which is what most current distributed systems do. Or we can stop and wait until we can talk to a true majority and find the fifth person, which is to say we're not going to be available and we're just going to stop until the partition heals.
So why does this matter? I mean, if all in the network state at the bottom has to do with is strictly on the bottom and it hasn't changed, then it's actually right.
Well, so keep in mind, these controllers are logically centralized. So unless you do something very fancy to make sure that the controllers on the bottom are just managing state for the bottom and the controllers on the top are just managing state for the top, which I'll get to later in the talk, you can start doing that, then this is fine. There is always going to be some state which is global, and that state is going to always have issues. So it's just a really simple example, like, policy about reachability for network virtualization is going to be stored, it doesn't really be associated with any particular switch, and so if you change that policy, you can result in inconsistent enforcement of of basically reachability between different groups until the partition heals. And I don't know of a good way to logically partition that kind of state across your network. You can certainly do heuristics which will help you some of the time, but the key point is there is no heuristic that's going to save you all of the time. So the CAP theorem was conjectured by Eric Brewer in 2000, proved by other people in 2002, and it's too bad that the other people don't know. The other people are no longer, I think, remembered very much. But I think it's FLP. It's at Finch, Lynch, and anyway, case in point. I can't come up with the three names. Basically, it says that you can only get two of the three between consistency, availability, and partition tolerance in the general case. And so you're forced to choose either CP, in which case you're favoring consistency, but you're saying on the minority side of partition, you will not be able to make progress. So you will not be able to do anything, you will not be able to know that you're reading the right values, you will not be able to write values without becoming inconsistent. Or you can be AP and favor availability, which is to say that when the partition happens, and usually in these systems it's the whole time, we're just going to read and write as best we can and hope for the best. And the last one is sort of CA, and this is what you want to choose, right? I want to be consistent and available. The problem is that this is tantamount to assuming partitions don't happen. That is generally believed to be something you should not assume. But there's, I'm going to have some good pointers to all three of these ideas as we go through. So the other point I want to make is that in talking about majority and minority partitions, so in this case, like we have a majority partition on the top, it has enough people to make progress, everything is happy on this side. And on the bottom side we have minority partition, where writes break the consistency and reads can be stale, which also means that they break consistency in the most formal model. This is not required to happen. You can certainly have a network partition which splits your network into more than two pieces, in which case they're all minority partitions, and nobody can do anything. So this is where you get into trouble. The other thing which I want to point out is that, and this comes up because this is to some extent an approach that Google has taken a lot, is that if all of your clients are on the good side, or all the clients that you care about are on the good side, for instance, if you can redefine your clients, so your Google and all of your clients are virtual machines, and you can just declare the old virtual machine dead and instantiate a new version of it on the side that's happy, then this doesn't matter. And you can get around this partition issue because basically you can just declare I don't care about the other side of the partition. In practice, SDN, that's a harder thing to make because you can't just declare your switch is gone and instantiate a new version of that switch on the other side of the partition, because that doesn't make any sense. In particular, if the internet is on this side, which is what a lot of people use, and the service that you're offering is over the internet, that's sort of the case which Google is interested in, which is like, if the machines aren't reachable from the internet, they're not useful to me. So the partition which doesn't have the internet on it is dead, and just kill it all. And if both sides are attached to the internet, then why is there a partition? Just go through the internet. Something has gone very wrong. So I'm going to talk a little bit more in detail about how modern systems deal with the CAP theorem, and just sort of walk through what the current approaches are. Hopefully this will give you some idea of where we might try and make decisions inside of OpenDaylight. So the first thing people do is they favor availability. This is the AP's decision. This is basically when there is a partition, or in practice all of the time, you just read or write from as many controllers as you can and hope. Or in practice, you read and write from some fixed number and hope. And this is in practice how systems like Cassandra, MongoDB, and Dynamo work. I have a bunch of references at the end of this, but you could also Google any of these things, and you would find them. You lose consistency after one such write. And getting consistency back is very hard. And that is why in practice these systems don't even try to get consistency in a strong sense, because basically the first time you do something different than what the majority would do, which is that you suffer a partition, you break everything and you don't get it back, so why even bother? And so this makes them really, really, really hard to reason about and program against, because you have no idea if you're talking about the same thing, or if two different nodes will take the same action, or you can't reason about what any other controller is going to do. So unless you are the only person doing something, that's all you know. You know what you've done. You have no idea what other people are going to react to, what state they're seeing, and what they're going to do. And this is effectively just abandoning the idea of logically centralized. So if we want a logically centralized control plane, this doesn't give it to you, at least not without huge amounts of work. You can favor consistency, and this is when there's a partition, people on minority sides stop being able to write data and possibly get stale reads. And a lot of times systems will, in this mode, basically they'll allow reads and they might tell you that they're stale, but they just won't allow writes. And actually the particular definition of there's, I guess, linearizability doesn't support this, but a slight variant of linearizability, which is just whenever I do a read, I read the most recent write. I guess I read the most recent write from my side of the partition. That sort of holds up, and it's something people can sort of think about. You're not going to see any violations of sort of timelines. You're going to have a timeline that just stops, and you're reading from that stop timeline, but you're not necessarily reading different data. You're just sort of reading in the past. And sometimes people allow this, sometimes people don't. This means the minority sides aren't available for writes, and this can be fine as long as no clients you care about on the minority side, or if, say, you just declare the minority side to be the side without the internet, and you actually only care about the internet. That's less true of SDNs. As go ahead. It either can reach a majority of its either you can reach a majority of the controllers, or you can't. It doesn't actually. And that's defined with respect to some timeout. So if there's a long, and so one of the things that happens is and this is, I'm not getting into this in this talk, but there's something to know. The difference between slow and dead, or slow and on the other side of the partition, is strictly speaking impossible to tell. You just have to define something, which is what you believe. And so if it normally takes me 100 milliseconds to talk to my peers, I might say if I can't talk to you for a second, I'm going to declare that you are either dead or on the other side of the partition. I have no idea which. Or you're just something happened, it's taking you a second to respond. The trick is, and why this is so hard, is that you have to respond to all three of those in the same manner. And so you end up maybe declaring somebody dead on the other side of the partition when they're not, and they're just slow. Although if somebody is slow, you should really just declare them dead and be done with it, because slow nodes tend to continue to be slow and cause you more problems. But yes, you're right. Latency and availability are sort of really inherently entwined, because availability only has sense in the sense of a timeout. Right? If there's an infinite timeout, availability is always true. So that's where it gets thorny. And there's a paper called CAP 12 Years Later by Eric Brewer, which sort of goes into some of these. I'm going to talk about it a little bit later in the talk, but it's worth going and reading. So good examples of this are every system Google has built, so Chubby, Megastore, and Spanner, And Zookeeper, which is a clone of Chubby, and some SQL databases, or at least most SQL databases that are running in clusters, have a mode which does this. It turns out, actually, most of the time they don't run in that mode, but that's a whole separate thing. But sort of systems that want to have strong consistency do this. These are the systems that exist. The ones that Google has built usually have some trick laden in them, which is how they get around partitions when they do happen. And in particular, Chubby takes the point of view that, essentially, they will define the clients that are on the side of the partition that is a minority to be dead to them, and they will reinstantiate them somewhere else because the clients are basically jobs running on machines that can be moved around and declared to be dead. And this is called stoneth, or shoot the other node in the head, which is basically saying, like, if I can't talk to this person, I don't know whether they're dead or on the other side of the partition, and there's one really good way to tell if they're dead or on the other side of the partition, and that's to kill them. And at the point at which I declare them to be dead, then it's irrelevant. They're dead. They're not on the other side of the partition anymore. And when the partition heals, I will know that, and I will detect it, and I will not listen to them anymore. So what about CA? I mentioned, like, assuming partitions don't happen is a really bad idea. CA is assuming partitions will not happen. Generally, people think this is a bad idea. There is a great blog post that is about 8 years long and I don't know Afir's name, but this is basically, it says the network is reliable, and sort of the end result is they comb every single data set they could find publicly available to try and figure out what partitions happen, how they happen, why they happen, and what you could do to stop them. And they come to the conclusion that with good design and with some considerable extra expense, you can build networks where the probability of partition is smaller than the other things that are likely to go wrong in your network and cause you problems. So that is something you could go look at and read about and talk about. The one thing that I will say about this is that in general, systems that assume partitions won't happen can't promise you either consistency or availability if a partition does happen, because they're not built with that idea. So you're usually better off building a CP system unless it's horrible in terms of performance, and you can make it not in the common case. And then basically just have it be available when there aren't partitions. And when a partition does happen, you're assuming they won't anyway, so you won't care that it's not available when it doesn't happen. But in practice, when it does happen, because these things do eventually happen, you'll at least know what you're getting. So that's sort of the three main axes people can take and some pointers. And the slides should be available online, I think. And there's a whole bunch of references and stuff in the end of the talk if you want to go click on these links and follow them. Or you can just search for the network is a reliable Afir and you'll find it. So the last thing is, and this is sort of talking about Eric Brewer's CAP 12 years later, there's other fanciness you can do. There are sort of two really key takeaways from the CAP 12 year later paper, although you should just go read it. One of them is that the first thing is that people tend to interpret the CAP theorem to be stronger than it is. The first way that people typically do that is that linearizability is the only consistency model for which it says you can't have it. Linearizability happens to also be the only consistency model I know how to think about, and most programmers know how to think about, which is to say that, like, there is one timeline and everybody exists at some point along that timeline. So maybe that's not so bad, but that's the one thing. The second thing is that the CAP theorem sort of implies that you have to make this trade-off once when you write the system, and that must be the way. So that is the way the system acts the whole time. So some modern systems sort of dance around these requirements in order to do interesting stuff. So they do things like detect partitions, only sacrifice consistency during the partition, and then recover it when the partition heals. Of course, that involves basically understanding enough about how you're inconsistent to fix it when the partition heals, which is tricky, but it can be done. The second thing is you provide less than linearizability as a status. So linearizability is generally considered to be all reads get the most recent write, no matter where the most recent write was written from. And for instance, if you instead change that to all reads, all of the reads that you issue get all of the writes that you have issued. That can be provided without needing to, but you can do that with availability and partition tolerance. The problem is that, like, that means that you're in two different worlds where, like, two different nodes can basically have totally different ideas of what the system is doing, because David has seen all of his writes, I've seen all of my writes, but we haven't seen each other's writes, and the result is we're going to make different decisions if we get the same request and tell you different things. And so understanding these consistency models is somewhat painful, and I think as a platform, OpenDaylight owes it to our developers to try and give them the simplest thing we can, and that's really what I'm trying to get at in this talk. So that, I could have given the last part of that talk pretty much about anything in computing that happens today. It had nothing to do with SDN. I occasionally used the word controller. That was about it. So what in particular about SDN should we learn? And so here are some thoughts about SDN inconsistency from two people you should listen to. One of them is Martine, and the other one is me. This is Martine's quote, basically. So he starts off saying, like, basically, lots of people are trying to figure out the right controller. I think the controller doesn't matter. Our experience is applications are about 10 times harder to write. To me, that seems like he wrote the wrong controller, but that's a separate problem. But he sort of ends with this quote, which I really like, and I think we have found the hard problems are with distributed state, which are app-specific, and they're not really sure how the controller can help much. If you take off this last sentence, I agree with him 100%. I think we owe it to our developers and as a platform to try and make this easy for developers, but really I think that the point that you make, such as the distributed state is the really hard thing about getting SDN right, is the right point, and that's you know, so it's not just me that's saying this is the hard problem and this is where we need to be spending our time. So given this is the hard problem, what should we do? We have an open source project. We can do whatever we want to do. Let's just start walking through it. We need switches to work even if they're partitioned off. Like, I don't think anybody in this room would say, hey, if there's a partition, I think the people on the minority side, they shouldn't be allowed to talk to each other anymore. That's fine. Or, so that says we need availability, so we've got to pick AP over CP. Great. That decision is over. The problem is that AP means that we basically have to provide eventual consistency. This means the controller and the apps are really not logically centralized from the programmer's point of view. We've just given up one of the few promises that SDN was trying to make, which is that we have a logically centralized control plane. So maybe this is what Martine was talking about. So basically, let's look at some other places to try and figure out what they're doing and see if they have anything to offer. Floodlight, and I realize somebody corrected me, this is not Floodlight, this is the big switch controller. And I think it's also the controller which is committed to, which is the OS, the network platform. If you do git clone, whatever it is, networkplatform.git, you will get a controller which is built against Cassandra. And it is based on Floodlight. Cassandra is AP, so it deals with eventual consistency. I think this is a terrible idea. There's a really long discussion on the mailing list between me and Rob Adams at Big Switch, which is worth going and reading if you're curious, which goes back and forth about, you know, why they chose this model, what the implications of that model are for their application designs, et cetera, et cetera, et cetera. So the other thing which I actually know about in terms of other controllers is Onos. And this is done by the OnLab people that are half Stanford, half something. I don't really understand exactly what their affiliation is. They use Zookeeper, which is a CP system, to map switches onto controller instances. And then instances own all the state for their switches. There's a whole presentation about this to the OpenDaylight technical workstream call on September 30th. If you search for OpenDaylight tech workstream, and all of the things are there, including WebEx replays, so you can just go watch the video if you want to go watch it. The two things which I want to point out about this is, one, I have no idea what they do about global state, which is sort of, you know, they do the logical thing in partitioning their local state when it's localizable. That's the right thing to do. Also, this means if you have a partition and a switch comes up on the minority side of the partition, you cannot legally assign it a controller. So you can't use it. This might be okay if you think partitions are rare, and maybe that's what they're hoping, but it seems like you would like to be able to assign a controller to a switch when it comes up, regardless of where it comes up in the network, if it can reach a controller. And unless you do this differently than Zookeeper does it by default, you're not going to be able to do that. So neither of these things really offers us a good trade-off. So what can we do? We want to make it easy for programmers to program against this, or at least easier for programmers to program at this. We want network connectivity and services to be on both sides of the partition, even if a partition happens. And the cap says we can't have it all the time, or we can't have all of it all the time. So we need to look at some of this fanciness that I mentioned before. I'm going to talk about two pieces of fanciness quickly. One of them is forking timeline consistency, and the second one is really about trying to partition the network and partition state in a way that we can work with. So forking timeline consistency, and this is my term. I don't know if there's a formal term for this or not. If there is, somebody tell me after the talk. But basically the idea is when there is a partition, the minority side forks after some sentinel timeout, say a second, and declares a new group by fiat. Just says like, and so in this case I'm going to call it orange. So you can see that the top side, as far as it's concerned, the bottom 4 nodes are dead. The bottom side, as far as it's concerned, the top 5 nodes are dead. The top side is going to be just fine. It has a majority. It keeps on chugging along. I could have colored that blue. I colored it green just to be able to refer to different things. The orange side isn't going to be able to make progress because they don't have a majority to do. what they can do is they can, by fiat, declare these other guys, I don't know what they are. Our group is 4 nodes, and it's these 4 nodes. They basically ask, everybody that can hear me, tell me who you are. I'm going to put you in the new group. I'm going to put a new timestamp in the ground, and I'm going to say, the last thing we heard was the last blue box. The next thing the first orange box is we forked, we went rogue, and here are the people we went rogue with, and then we're going to keep going. The good news is that we now have 2 at least internally consistent timelines. So we don't have one consistent world, but we at least have 2 worlds that are consistent in and of themselves. And then later on, when the partition heals, somebody has to fix the mess, but the mess is at least somewhat contained. So we have 2 internally consistent things. Somebody has to figure out how to merge things. This is often easier than you'd expect. The example I like to give is if the state you are maintaining was NAT translation tables, you can walk through in your head how you have source IP, you have source IP, destination IP, and source port and destination port, and that's what you're mapping on. And either you have 2 entries that overlap, in which case you tend to TCP reset in both directions because something went really wrong, or you just merge the 2. And so most state, when you think about it at an application level, there's a somewhat straightforward way to fix what's gone wrong. And there are actually J groups, there's sort of 4 differences here. We use InfiniSpan in OpenDaylight today. InfiniSpan is based on, and by based on, I mean corrupts and removes all of the good things from J groups. And J groups actually has view changes and view merges, which are exactly what I'm talking about here, but they're not exposed up through InfiniSpan. And so, but for what it's worth, I think these view merges, or these partition merges, are actually more tenable than you might think. You can provide a library of them to application developers, and so in the common case, basically it's just you pick one of the 6, pick a random one when they conflict, pick the left one when they conflict, pick the most recent one when they conflict in logical time. There's a series of policies which I think if you got 5 of them, might work for almost everything that people do. That remains to be seen, but I think we could go try. So the second thing is about exploiting locality, and this is about sort of what the first question was about, which is basically if you can just partition your network into regions, and then you can assign the data to regions. So we'll partition our network into regions, we assign controllers to regions, probably those controllers are in those regions, so they're less likely to partition from people. Then we can make it so that way partitions are rare inside a region. I think I even, partitions are rare inside of a region. And so as a consequence, when partitions happen, typically all the state for that region is stored near that region, and they continue to work correctly, and actually they're allowed to update their state because they own it, so they can even write to it. And hopefully nobody will need to read from it because they're in different regions. And so basically what this amounts to is you hope that partitions don't happen north-south here, and because you've done it right, and more communication goes north-south between the controllers and their regions, and much less communication happens east-west between your controllers, so the result is at least in the common case you might not be as screwed. This is loosely what ONOS does. Another point is that the MD-SAL in OpenDaylight might actually really nicely give you the metadata you need about what your state is to be able to assign state to regions and actually define your regions programmatically and then basically just have it automatically freshened out. That is by no means implemented, but it is something you could think about. As I said before, if you locate controllers near their devices, this has other advantages. So you minimize the latency and possibly improve performance because you're essentially keeping actions close to them. You lower the risk of separating devices from their controllers, so you increase fault tolerance. If you can also, you can make then you can make this recursively. In your small partitions, you can then make these clusters, and you can try and use similar techniques. And so again, this doesn't solve the problem, but it might make it less likely to bite you. So the next thing I talk about is a little bit about scale out, but before I go there, I just want to open it up and take questions. I think we have 3 minutes left, so I can talk a little bit about scale out or I cannot, and I think scale out is the last topic that I really have. The last thing which I have is that there's a design seminar in the Napa room after lunch, which is, or a design summit is the other half, so about this. So if you're curious about what we're going to do in OpenDaylight and want to help, or want to offer your 2 cents, or want to tell me I'm an idiot, 1:30 in the Napa room is the right place to come. So in the 3 minutes I have left, anybody want to ask?
So in all the pictures that you showed of partition, you talk about it as this, like the network is this atomic thing that we just slice in half in a 2 atomic ring. When in reality, you could have like partial connectivity, so there's not like a partition anymore. There's just some weird inability to communicate with subsets of nodes, right?
So this is the asymmetric connectivity, and asymmetric connectivity is a royal pain in the ass. I believe that's a technical term. There are ways to deal with it. The good news is that partition-tolerant systems are somewhat resistant to that, aside from the fact that they might declare a partition when they might not be available, even though they could be available by detouring traffic through some other point. So they'll be correct. They might not be as available as they could be in the maximal case. I would like to treat that problem as independent from this. You can also do things like try and detour traffic, which is to see if there's somebody else. You can put a layer on top of this, which says if there's somebody else who I can talk to, can then talk to that person, can I set up effectively a tunnel through them? You can certainly do that, and it can be done independently of everything else and just wired in as a virtual link that you can talk through. And so I think separating that concern from the logical view, which is that things should be symmetric, is probably useful because it stops me from having my head explode when I think about it. So if you're an app, so the question was, you don't have to pick one consistency model for the entire controller. You can do it per module or per app. And the answer to that question is yes. But if you depend on somebody that has a different consistency model than you do, that is likely to bite you. So in general, you probably want to be able to ask the question of all of the modules that I'm depending on, what are the consistency properties they are providing to me? And as a consequence, what does that mean about what consistency model I should ask for and what I can actually do for you? And that is a totally open question inside of OpenDaylight as to how it is that you go deal with that problem. If you're an app at the top, I absolutely agree that it doesn't matter. Like if nobody is consuming your stuff, if you're just messing around, pick whatever consistency model makes you happy. But if you're like a service, like topology, I damn well better be able to understand what your consistency model is, so that way I understand what I'm programming against. Okay. It's 12:10, so I'm not going to stand between you guys and lunch. Thanks for coming. Centralized control plane, because that's what we want. And in practice, we built the distributed control plane out of a sort of a distributed cluster of controllers when we're building SDN controllers as a general rule. One, so we can tolerate faults. Two, so we can maybe scale out performance. Although I've heard a lot of people talking about that, and less people actually showing me that I can't, that I need to do that. In particular, like Dave Ericsson in the front row built a controller that does 10 million flow operations per second on a single server. So if you're planning on, maybe scale out might not be as important, but I'll talk a little bit about that. And then lastly, and this is going to sort of a forward reference to things I'm going to talk about in the talk, if you have a network partition, you hopefully distribute your controllers such that there is a controller on both sides of your partition at the very least. So that way, the devices which are left on the other side can still do something useful. So I'm going to do something probably I shouldn't do in a talk, but I'm basically going to give a 20-minute distributed systems lecture because I've discovered that distributed systems is not very well understood. And hopefully this will let you in 20 minutes sort of get the equivalent of what you would have remembered if you had taken a distributed systems in class in undergrad or maybe in grad school. And so before I dive into that, I'm just going to say a couple of things. First of all, traditionally when people talk about roundings, a majority is 5, it's not 6, but we'll get into that. But if you have N controllers and they all sort of start off sharing the same idea of what the network looks like, let's say that it's green, then it's all consistent and everything is happy as long as your clients talk to the same controller. They'll get the same idea. So if you have 2 different clients, they both talk to the same controller, same as before, they're both going to find out the same answer to whatever question they might ask. Problems start coming up in this kind of model when clients are talking to different controllers, which is what you actually want to happen, right? You want to have some of your switches bound to different controllers, preferably ones close to them, or at least be able to fail over to ones close to them, so that way if a partition happens, they get that, or maybe they get better latency, or maybe you're just lose less of your network if one controller goes down, so that you minimize the impact of a single controller going down, et cetera. And so in this case, if everybody starts off thinking it's green, everything is fine so far. But if this first client, say it's a switch, updates some state about the network, it says a port has gone down. And so it updates it, and so now the state of this one controller is blue, representing that something's changed. And it's going to actually get that back, so in fact it sees the network as being blue, whatever that means. That's not going to help this bottom guy. This bottom guy is going to go ask some other controller, and he's going to get back the answer that it's still green. And this is sort of, right, this is the problem we're trying to solve. We have different people doing different things, trying to sort of coordinate their actions, and without some coordination, we're going to get totally different answers, and nobody's going to be able to figure out how to reason about it. So the really simple first fix that people go to use this, and it's not all that simple in practice, but it's simple in concept. You can think of this as Paxos, or you can think about it as two-phase commit, or I guess it's three-phase commit is the other one, is that if each client talks to a majority of the controllers, things are okay. So just to give you an example, let's say this first client, so everybody thinks it's green at the moment, this first client is going to pick a majority, let's say these 5. And he's going to talk to these 5, and he's going to tell them all about his update to the network. This port has gone down, for instance. And now all 5 of these people know that, in fact, the state of the network has changed, which now this port is down, it's blue. The great part is that if the second client also picks a majority, by definition, those 2 majorities will overlap at least one node. So when it asks the question, what is the state of the network, it will get back 5 answers, one of which is the correct answer. And because we are going to use logical timestamps inside of this, we actually know which one is right. So we have data that says the blue thing happened after the green thing, so we can actually go and say blue is the right answer, and we know about it. And so these majorities are great. So right, it's great. Now we have something acting logically as one, and distributed systems, they talk about replicated state machines. I'm not going to talk about replicated state machines, but if you want to go read about them, what I'm saying is actually applicable to them just fine. People typically talk about clients and servers. I'm not going to talk about clients and servers. I'm going to talk about clients and controllers, because I just want to keep us thinking that we're talking about SDN, not an abstract thing. And when I say client, I don't mean somebody with a web browser. I mean a switch or a REST, or somebody calling the REST API or tickling things. So these are sort of people consuming services that the controller is offering. The key idea here is that things are really easy when there's one controller. If 2 clients talk to a controller, it's the same controller, because there's only one. So it's right there. And if they go and ask it something, like say, what color is it? And the server thinks it's green, the controller thinks it's green, it's going to tell both people that, in fact, it is green. They don't have to worry about what other else might happen. So this is really what we want. This is the model that we are going for. This is what people can understand, they can program against, they can deal with, and they can reason about. So the real question comes down to, how do we get n different controllers to behave as though they are one controller? So let's say we have a collection of 9 controllers. I use 9 because you're going to have majorities of things, and it's easier when I don't have to do weird. Last night I was working on this talk, and I was looking in sched.org, and I found out that you can look at your popularity of your talks. And this was listed as 47th out of 50 talks in terms of who had signed up to come to it. So I'm glad that there's actually some people here. Maybe waiting 13 minutes was good. I'm going to talk about consistency trade-offs for SDN controllers. And this is sort of, think about it as clustering, HA, distribution, logically centralized, whatever you want to call it. That's why I'm going to sort of try and talk about what we can and can't do, and why this is sort of a fruitful area to go work on. So I'm putting this slide up not to argue about it, but so don't argue with me about it. But I admit there are lots of different definitions of SDN, but my personal sort of 3 promises that SDN or 3 premises that SDN went through was, 1, sort of separation of the control plane from the data plane. That's the ONF standard definition. 2nd was the logical centralization of the control plane. And last was sort of common abstractions for network devices. This talk is going to be all about logical centralization of the control plane, and in particular, the logical part of the logical centralization of the control plane. And so just before I dive into that, I want to go over why it is that we can't have an actually